Hello and welcome to the first of three lectures on mathematical methods in physics. So, unfortunately, even though this is a conceptual class, I would say that one of the main assumptions of physics is that the reality can be explained by mathematics. So, in order to understand physics, we will have to go over a little bit of math. It shouldn't be too hard, and what goes into these videos is going to be the hardest that is going to come up in class, but it is something that we need to do. So, the first thing that we need to talk about is defining the terms functions and variables. So, what are functions and variables? A function tells you the relationship between two or more quantities. For example, the amount of interest accrued in your credit card can be described as a function of time. So, for example, if you get a student loan or a mortgage, they'll give you a output or they'll give you a paper that will tell you how much you owe at any given time. So in 2035, you may own $10,000. In 2045, you may owe $5,700. So the function is the output. It tells you how much you owe, and the variable or what the function depends on is called time. And it's called a variable because the input can vary. It can be 1 year out, it can be 5 years out, it can be 100 years out, it can be any number, and then the function is going to tell you some information about how what you're looking at relates to this other thing that you're looking at. So in this case, it's the interest accrued on your credit card or on a mortgage or on student loan versus time, which is your independent variable. Is called an independent variable, and then the dependent variable is the function, which is called, which would be the amount of money that you owe. So variables tend to be written as letters or Greek letters, and the function with a variable is generally written as f of x or g of x or some function, some letter, parentheses of the variable, uh, but it can also be treated as its own variable because, which is called a dependent variable versus the independent variable, which is what you can change in order to get your value that you want to get, or which is what you can change in order to check at what time you were going to have this amount of money. The time is the independent variable, and the function, the amount of money that you have, is the dependent variable. So a graph can also show you the relationship between a function and its variable laid out over many different values of the variable. So the goal of a scientist is to come up with as simple of a mathematical relationship between the variables as possible. Sometimes this is difficult because of confounding circumstances, which can either be controlled or accounted for when we come up with our function. So for example, this is the Scripps Oceanography's atmospheric CO2 at the Hawaiian Mauna Loa Observatory. So as you can see, it goes up, and we can tell the raw function is going to be the amount of CO2 versus the year, where the year is your independent variable and the amount of CO2 is your dependent variable. So what you will notice here is that it goes up and down kind of like a sawtooth pattern. For each year, it will go up and then it will go down and it will go up and it will go down. So why is this? This is because trees and other plants will absorb CO2 during the spring and summer and will not absorb CO2 during the fall and winter because they're dead or they're I'm not sure what the term is. The animal equivalent would be hibernating. But when you want to look at the overall trend, you need to account for this variation in the red lines. So the overall trend is going to be the black line that you see. And when we come up with the scientific theory, when we try to do a fitting of the uh, variable or of the dependent versus the independent variables, we are going to try to account for this variation that we see that's not going to tell us the true story of how CO2 is changing by year to year because you have this confounding variable of the CO2 going up and down according to the number of trees in the area. So the first function that we're going to look at is called a linear function, which is when y is proportional to x plus some additive factor, where y is the dependent variable and x is the independent variable. So what this means is that the slope of a line when you draw the graph is the same, or is always going to be constant, or in another way that we can write it or explain it, that the rate of change is the same. So, for example, if you had your credit card debt be linear instead of exponential like it actually tends to be, what you would see is that from 2024 to 2025, it would go up by 500 dollars, and then from 2025 to 2026, it would also go up to by $500. From 2026 to 2027, it would go up by $500. So the rate of change, how much changes in a year, is constant for a linear function. So how we solve for these variables, how we solve for these functions, we have examples on here of Newton's second law, F equals ma, where m is mass and a is acceleration. So if we want to solve for F, we say F is equal to 2 times 0.5 if, okay, just a second. If m is equal to 2 and a is equal to 0.5. So all we do is we take the variable and plug in a number and take the other variable and plug in a number. So f is equal to 2 times 0.5, which is equal to 1. Yeah. But if instead acceleration was equal to 4, we would say f equals 2 times 4, and that would give us 8. This function tells us how these two variables relate to each other, but we can change the variables and it will tell us how changing one variable changes the other. The second type is y equals x squared, is a quadratic function where instead of the dependent variable depending on linearly, so that the change is always constant, the slope is always constant, and the change in whatchamacallit, in the rate of change is always constant. Instead, you have it depending on the dependent variable, depending on the independent variable, as 1. So the second type of function that we're going to talk about is the quadratic function, where the dependent variable depends on the independent variable times it to the squared power. So I am assuming that you know all these types of uh, arithmetic, that you know how to do exponents and multiplication and addition. But if you don't, then you can just go on Google or go on your calculator or go on Wolfram Alpha and type it in, and it will put out the answer for you. But a quadratic function, an example of a quadratic function in physics is kinetic energy, where kinetic energy is related to the speed squared. So for k equals 1/2 mv squared, we have for m equals 2 and v equals 3, we have k equals 1/2 2 times 3 squared, which is, if we're going according to the order of operations, 1/2 2 times 9, which is equal to 1 times 9 is equal to 9. And then that's basically what you see when you have this relationship where it's proportional to the variable squared. You see that the function looks like this shape, which is called a parabola. The next thing that we're going to type of function that we're going to talk about is an exponential function, which is, instead of being x squared or x cubed or whatever, it's 2 to the x. So you start out with, or it's some number, not necessarily 2, to the x. So you start out with a number, or you start out at 1, and then for 2 to the x, you go at x equals 1, it's going to be 2 to the first power, which is going to be 2. At x to the equals 2, it's going to be 2 to the second power, which is 4. At x equals 3, it's going to be 2 to the third power, which is going to be 8. And it's just builds and builds and builds like this. But if you have a number that's smaller than 1, such as 0.5, then it's going to go down. It's going to get smaller and smaller and approach 0 instead of approaching infinity as x gets bigger and bigger. So a physics example of this is the half-life of a radioactive material. So n equals n naught times 1/2 t over lambda. So for n naught equals 8,000, lambda equals 2, and t equals 4, we have n equals 8,000 1/2 4 over 2, which is going to be 8,000 times 1/2 times to the second power, which is equal to 8,000 times 1/4 is equal to 2,000. So the last function that I want to talk about are sines and cosine functions, which are related to trigonometry and come up pretty often even when you're not talking about triangles, because of a relationship that comes about in differential calculus that I'm not going to get into here. But the motion of an oscillating spring doesn't really have to do with triangles, but still follows this sine and cosine function. So, for example, you have time of flight of a projectile, t versus 2v over g sine theta, where v equals 2, g equals 10, and theta equals 30 degrees. So this time of flight is going to be equal to 2 times 2 over 10 times sine of 30 degrees is going to be equal to 2 times 2 over 10 times sine, or I already put sine of 30 degrees, but the sine of 30 degrees is 1/2. So this is going to be equal to 4 over 10 times 1/2 is equal to 4 over 20 is equal to 1/5. So hopefully this gives you a good idea of how to work with variables. Basically, when you see a variable, all you have to do is plug in the number that it corresponds to, and that will tell you how something else is changing dependent on that variable. So thank you very much. I am going to move on now to the next math lecture.